Hello everyone, this is lecture 19, Lagrange multipliers. One of many challenges in economics and marketing is predicting the behavior of consumers. Basic models of consumer behavior often involve a utility functions that expresses consumers' combined preference for several different amenities. For example, a simple utility functions might have the form of capital U equal to f of L, G, where L represents the amount of leisure time and G represents the number of consumable goods. Consumers try to maximize their utility function, but they do so under certain constraints on the variables of the problem. For instance, increasing leisure time may increase utility, but leisure time produces no income for consumable goods. Similarly, consumable goods may also increase utility, but they require income, which reduces leisure time. We first develop a general method for solving such constraint optimization problems, then return to economics problem later. And that is the idea of this lecture. That is, we try to develop a general method for solving such constraint optimization problems. And hopefully at the end of this lecture, you could be able to use the method of Lagrange multipliers to solve optimization problems with one constraint. So the basic idea is that we're going to start with a typical constraint optimization problem with two independent variables and give its method of solutions. So the idea is that we seek maximum and or minimum values of a differentiable objective function f with the form of z equal to f of x comma y, with restrictions that x and y must lie on the constraint curve c, present in this manner, and the curve c is in the xy plane given by the equation of the form g of x comma y equal to 0. So consider this figure. The figure shows the details of a typical situation in which we assume the green level curves of the function f have increasing z values moving away from the origins. As you can see here, for this curve z is equal to 0, this curve z is equal to 1, this curve z is equal to 2, so on and so forth. Now imagine moving along the red constraint curve, and the curve is parameterized using the equation g of x comma y equal to 0 toward the point P equal to a comma b. So let's assume that you're going to start at this point and you're going to move along this red curve toward the point P equal to a comma b. As we approach P, from either side of P, the values of f evaluated as c increase. As you can see, if you stand here and then move to this point, then the value of z increase from 0 to 1 to 2, so on and so forth. And as we move past P along C, if we continue moving in these directions toward P and then get past P and moving this way, as you can see, the value of Z or the value of F decreases. So what is special about the point P at which F appears to have a local maximum value on C? So we know that at any point P equal to a comma b on the level curve of F, the line tangent to the level curve at P is orthogonal to the gradient vector, gradient of F evaluated at a comma b. I show using this vector. The figure also suggests that the line tangent to the level curve of f at P is tangent to the constraint curve C at P. This observation implies that the gradient of f evaluated at AB is also orthogonal to the line tangent to the curve C at the point P equal to a comma b. So that is the gradient of the function not only orthogonal to the tangent vector of the level curve at the point of consideration, is also orthogonal to the line tangent to the curve C at the point of considerations. Now we're going to make one more observation from this particular figure. That is, the constraint curve C is just one level curve of the function z equal to g of x comma y. So the line tangent to the curve C at the point P equal to a comma b is orthogonal to the gradient vector of the function g evaluated at a comma b. We have now found two different vectors, gradient of f and gradient of g, that are both orthogonal to the line tangent to the level curve C at the point P equal to a comma b, as shown in this figure. Therefore, these two gradient vectors are parallel to one another. So these properties characterize the point P at which f has a local extremum, or local maximum, or local minimum on the constraint curve. They are the basis of the method of Lagrange multipliers that we now formalize. So from our discussions, we see that f at 10 is maximum value on the constraint curve at P. So f at 10 is max value on the constraint curve. At P. And also from our discussions, we show that two vectors, the gradient of f and the gradient of g, are both orthogonal to the line tangent to the level curve c, so the curve in red, at the point a, comma b. Therefore, we can say that the gradient of f evaluated at the point a, comma b is parallel to the gradient of g evaluated at the point a, comma b. So now we're going to jump into the method of Lagrange multipliers with two independent variables and one constraint. So let's assume f of x, y and g of x, y are differentiable functions. If f of x, y has a local max or a local minimum on the constraint curve, given as g of x, y equal to 0 at the point x0, y0, and if the gradient of g evaluated at x0, y0 different from 0, then there is a scalar lambda such that the gradient of f evaluated at x0, y0 is equal to lambda times the gradient of g evaluated at x0, y0. We can come up with this particular formula because we showed that on the red curve C and at the point of considerations a, b or x0, y0, there are two gradient vectors. There are two vectors that are orthogonal to the line tangent to the red curve. And the two vectors are gradient of f and gradient of g. Therefore, these two vectors are parallel to one another. In other words, one vector can be written as the constant multiple of the other vector. Therefore, the formula gradient of f equal to lambda times gradient of g. And to locate the absolute maximum and minimum values of f subject to the constraint of g of xy equal to 0, we're going to carry out the following step. So the first step is to find the value of x, y, and lambda if they exist that satisfy the equations. So to locate the absolute max and mean value of f subject to the constraint g of x, y equal to 0, we carry out the following step. So the first step is to find the values of x, y, and lambda if they exist that satisfy the equations. Gradient of f evaluated at x, y equal to lambda times the gradient of g evaluated at x, y, as well as the constraint equations of g of x, y equal to 0. The second step is to evaluate the function f at the value x, y that you found in step 1, and at the endpoint of the constraint curve if they exist. Then select the largest and the smallest corresponding functions in value. These values are absolute maximum and minimum values of f subject to the constraint. So the second step is evaluate f at the values x, y found in step 1 and at the endpoint of the constraint curve. If they exist. Now, if you have the largest value, this is going to imply the absolute maximum of f. And if you have the smallest value, which indicates the absolute minimum value of f. Alright, so that is the procedures that we're going to follow to find the absolute maximum and absolute minimum of the function subject to the constraint of g of x, y equal to 0.